fermions because I'm going to use these things. The model that describes gapless and gapped phases depending on the value of the parameters. The action, we defined that, whatever is in between these two sides is the Green's function to the -1. And this matrix M is just a diagonal of the velocities, just taking care of, it's a diagonal matrix taking care of the velocities. Expectation value to first order in the external field of the current is governed by the polarization function, and it's given by this expression here. So we calculated that for a model that's a Schringer model, but you just have to think that's just two chiral fermions in one dimension, so just do things like this. And we saw that when we calculated this polarization function, it actually it was logarithmically divergent just because of power counting in this other equation here. And we saw that it was dependent on how we regularize the theory. But we fixed this ambiguity by but considering gauge invariance that imposes, charge conservation that imposes that this divergence has to be 0, which in momentum space means that the polarization function times the momentum has to be 0, and this fixes A to be 1. Okay, so now I'm going to go on and consider what's called the chiral Schringer model, which is a very simple variation of this. It's basically the same thing, but now I'm gonna have a projector here in the middle with the A, gamma mu, A mu, psi. So this thing is, remember, 1 plus gamma 5 over 2. Maybe I'll put a 2 here. So it just projects, it's kind of making sure that,
Just a short question regarding the stuff on before.
Yeah.
It looks very similar to the free photon program.
Yeah.
What is the difference? Because you did a very lengthy calculation to arrive at it.
Yeah, I mean, it's just a free photon propagator. It's just that, it's what do you mean by free?
That's what you get when you just have a signal, when you consider the electromagnetic field and invert the
Right. So so I'm considering the first, how the electromagnetic field gets screened by this electrons, right? It's just that calculation.
Okay, the screening is in the 1 over pi.
Yeah. So I guess you can relate pi to the conductivity, and the conductivity to the epsilon, to the dielectric function. The way you do that is, okay. So the imaginary function of the 0 component over omega, I think, is, let me say q to 0. I think this is the real part of the conductivity, some function of frequency. Let's see. So it's like J0, Y00, E0. Actually, this might be IJ. Right. So this is IJ, IJ, partial T that becomes an omega. Yeah, something like this. And then, this is related to the dielectric function. But okay, yeah, so this is what you usually would calculate for, in a many-body textbook, you would calculate this for p squared over 2m. Somehow you would find, Thomas Fermi screening and so on. So that's exactly what I'm doing. Here, there's no screening because, this is kind of chiral fermion, so there's no real, in like, for example, if you calculate this for graphene, there's no density of states at the Fermi level and so on. But okay, but that's a different story. Yeah, so this of course is related to physical observables. I mean, this is just the current. This is linear response in the current, so that's important to keep in mind. So now I do the same calculation, and I arrive to the following thing. Let's see. So, I separate again finite and infinite, and the finite part looks a bit weird, but let me just write it down, and then I'll explain. Beta. Actually, these indices look very. Oh no, wait. Beta, nu. Beta, nu. Okay, so I think I didn't actually say yesterday what this guy was, but it's just it's just a metric. It's just a diagonal matrix that I chose to be this with this signature. So a bunch of minus a 1 and then 3 minus 1s. So just defining the product of 2 4 vectors. And this object here is the Levi-Civita tensor is just non-zero when these 2 indices are different. So, and you have to choose a convention. So you might choose this, and then all the rest are 0. So I remember I just have 2 indices because I'm in 1 plus 1. Now, now this is good because like whenever you see this guy appearing, it's good for topological stuff because it means that it doesn't depend on the metric. It's independent of the geometry. So this means that whenever you get Levi-Civita tensors, something topological has happened. I don't know why this is. Am I doing something wrong or yes? Okay, I'll be very adiabatic. Okay, it's not. I don't think it's my fault. Okay, so okay, A or yes. Let's see if this is better. Okay. Okay, so I have this weird form. It doesn't really matter what form it is. What matters is that there's also, oh my goodness. Okay, how about here? Okay, there's also a term that depends on the regularization. So it's this A appearing here again. But now, if I compute this P mu nu, I find this just by substitution. Just plugging this back in. This is really annoying. But okay. But you find that no matter what value of A I choose, this is not 0. So it means that gauge invariance actually does not fix the ambiguity. What fixes the ambiguity is that, in a lattice, we always will have 2 copies of this theory because what we're seeing here is that we're kind of violating charge conservation of a single species of movers, either right or left. I guess I chose right here. And so what we're seeing is that in a way the chiral anomaly in 1 plus 1 is regularization dependent and is actually not fixed by any value of A. But since we know that fermions come in pairs, once I add this model with PR to the model with P left, I recover the Schringer model and I fix again A, and everything is fine again. So in this sense, the way to fix this ambiguity is noticing that in a lattice model I would always have 2 copies of this theory, one with left, one with right. And that will solve the problem. So charge will still be conserved. But notice that individually, the charge, the left and right movers, the charge of the number of left and the number of right are not independently conserved. So this means that, in fact, I can write an equation that is, current of the left, current of the right, and this would be, in this case, proportional to the electric field, actually. This, I mean, I have not derived that, but you can see this intuitively because, let's say I fill this system up to here, and then I add an electric field. What's an electric field? An electric field is just shifting K to K minus ET. So this is like, well, I just have one K, so this is like A1, like the first component of the gauge field. And so what I'm doing is that for the right, let's say, for the right movers, I'm moving some guys up. Well, let me draw it in another color. So as time goes by, I'm increasing the population of right movers and decreasing the population of left movers. And so I end up, so total charge is conserved because whatever I lose here, I gain here, but independently the charges are not conserved. So, and the difference between them is proportional to the electric field. So that's in a nutshell, the chiral anomaly in 1 + 1. That's kind of what we're seeing here. Okay. So now we're going to go to the more interesting case, which is this model here. And again, I'm going to calculate this pi object. Okay? Let's see. So okay, so far, nothing really drastic has happened because of this regularization somehow, or nothing really, we are always fixed things. We've always fixed the ambiguity with either charge conservation or the fact that both are, we know that both fermions appear in the lattice. But here, this example is going to be different. So I'm going to get this theory. And I'm going to calculate the pi. So the pi is written here. I don't know if everybody can see it. I guess so. I can write it again. So it's an integral. It depends on p. Actually, I'm going to say that it depends on b, the vector that breaks Lorentz invariance. Whoops. I'm writing pi. So it's the trace g of k gamma mu g of k plus p gamma nu. And that's it. And maybe like a 2 pi over 4. And this, I'm gonna remind everybody that these guys depend on B. Actually, I might write them explicitly. They depend on K, depend on B, the Green's functions. And I can write them like this. It's just the inverse of that thing. So it's just this. And so if I'm calculating the linear response of this theory, I'm calculating how a vial responds to an electromagnetic field. So I guess it reacts when I say something exciting. And this is going to depend on B, right? Now, for the purpose of this, no? Oh yeah, that's true. Okay. So I have to say all the time exciting things. Okay, so right. So I guess the pi mu nu I can separate it into parts that are even under exchange of mu and nu, and parts that are odd under exchange of mu and nu. I think it's actually a cable, but okay. And so I'm going to focus on the p odd. So meaning the part of I think it's definitely this stupid cable. Let me just do this. Let's see if it works. I'm really sorry. Okay, let's do this. So this means that this part, to be odd in mu and nu, I just defined the Levi-Civita tensor. You can show that this guy is going to have the following form. P rho B sigma, B sigma, and then some scalar function that's going to depend on P, B, and M. And now I want to ask what is this guy? Now, some people, like the first attempts to calculate this thing, calculated this k perturbatively in B, so to linear order in B. But in fact, you can calculate it to all orders in B. And this was done by a Spanish physicist, actually, for the first time. It's Manuel Pérez Victoria. I think he's a professor in Valencia or some place. But he was at MIT at some point, and where he calculated this, because all these theories were worked out by Jacques, and I guess he was motivated by his works too. And he arrived to the following expression for pi mu nu, odd. So you kind of follow his PRL and find this this object, sigma. It's a calculation that doesn't really add much to the story. Just, again, it has a part that depends on the regularization and a part that does not. And so one can isolate those. He actually did. And you get the following expression. So other people had calculated this to linear order or to all orders, but assuming some condition between B and M, but this guy did it for all cases. And he found the following result. He found a constant that is regularization dependent when we're in the gapped phase. So remember that when this condition was true, I hope I wrote it right. No, it's actually the other way around. Is it? Okay, anyway, so from when the theory is gapped, you find just a result like this, just a vector that depends on the regularization. And if the theory is gapless, you find this object minus this constant that depends on the regularization. And so you should recognize this already, because I have it written right here. Okay, this is not good. Okay, so you can recognize this object already. So this is, the Weyl node separation appears in the expression of the polarization. So if we only, okay, which is just remove it completely. Engineering technique. Yeah, I think it's when I. Okay. Anyway. Oh, because I think they're recording this. It's, I can say hi to my mom and stuff. Okay, so point is that when you're calculating J, so let's write J for a particular case. Okay, so maybe this will make it clearer. So what is J? Let me focus on the ith component. So just a spatial part of J. This would mean that I have I here in this index, so I here, I. And these guys I can choose, they have to be different. All of them have to be different. And so I'm going to choose to write the following component. So I want this to be spatial. I want this to be I, J, K. Okay, good. This one. So this would be pi P0 B K times let's say I'm just focusing on this thing just to show you what this response really means. Okay, so I wrote some component of the current that depends on P0. P0 is just the frequency actually. Then some spatial part of the B, so the vial node separation in momentum space, and then I have the A, right? Because I had the A here too. Now this and this I can write as the electric field, because in some gauge, right? And this just is taking a vector product of B and the electric field. So actually the response, J, I, or vector J, is the vial node separation that I defined there, cross E. So this calculation has led to the following result. The Hall conductivity, because what's the Hall conductivity? Is the conductivity that is perpendicular to the electric field. The Hall conductivity is proportional to the vial node separation. This is a known result in vials. It comes out from this model. But this calculation also showed us that there's another object here that we have to define, because the Hall conductivity is a measurable quantity. So there's like an additional thing here, like an additional vector I'll call G, that I can add. And in principle, the calculation allows for this vector, and it depends on the regularizer. So how can we fix this? So in fact, the low energy theory can never really fix this. There is always an ambiguity, and the reason is the following. And it becomes clear when I write the effective action that I defined yesterday. So I'll erase this. Actually, I shouldn't have erased it, but okay. So the effective action, actually I'm going to write exactly the same thing, but okay. So the effective action, remember that was, the effective action is given by this object, essentially, schematically. So the effective action, or the odd part of the effective action, is something that looks like schematically epsilon B P, this object K, well, essentially what was written before, and then the A. So if I write it in so this we just found it was like C minus square root of 1 m squared over b squared for the gapless case. Now if I write it in real space, the P turns into a derivative, so this actually looks like this. B, so epsilon B A cross A partial A. Is this clear how I got this? So I'm just writing, so I calculated this, the odd part. There's an epsilon. I plug it in here. I get schematically this object, which is A, this A. Then I had P, the external momentum. And then I have to put this object inside it. Multiplying it. And then the other A. And so schematically it looks, in real space, it looks like a Chern-Simons term. This is called a Chern-Simons term. I guess it has popped up in some lectures. And one of the things of this Chern-Simons term is that it's not gauge invariant. So I can always add a surface term that changes the coefficient of this action. And that's exactly what you do in the Hall effect. There's, you can always add stuff at the boundary that changes your Hall conductivity by an integer. And in fact, so I'll do this here. In fact, we can relate to a general result to fix this C, or at least understand it physically, which is that the Hall conductivity of a three-dimensional system is in general, or can be written in general as this object. I guess there are many K's. What else can I use? Yeah, use this like face. Okay. So the whole conductivity of a three-dimensional system can always be written as E squared over H times some vector with units of momentum. And so Haldane gave us the expression for this Km in general for any system. And it looks like this. Contribution. So there's a contribution from the field bands, which is proportional to a lattice vector, actually. So that's why I call it G, because it's a reciprocal lattice vector. And there's a Fermi surface contribution that has some expression in terms of the Berry curvature, but it's not important for our purposes. So this you can understand in the fact that you get this, you can understand it the following way. Imagine you have a system, a 3D system that is a collection of 2D Hall effects stacked in some certain direction. And you want to calculate the whole conductivity of this. So each plane has E squared over H conductivity. And now in reciprocal space, the total conductivity would be Kz, an integral over Kz over this two-dimensional conductivity, E squared over H times the Chern number, which is what we learned from Evo. And so this gives, nothing here depends on Kz because these layers are completely decoupled. And so the total whole conductivity is just the stacking vector times the Chern number times E squared over H. So there's always the possibility that you have a system that's a 3D Hall insulator. So this gapped phase here actually secretly knows that it could be a trivial insulator with no Hall conductivity, or it could be a stacked version of 2D insulators. And that's what this C actually is. So it's quite physical. But you would never get this from the low energy theory because it's proportional to a reciprocal lattice vector. You would have to include it in the beginning. When you derive this model, you would have to declare that your gapped phase actually has a Hall conductivity, which is given by that G. And then you would recover the real result. So this calculation is always ambiguous up to a lattice vector, which is, it's reasonable because we're measuring a difference between two vial nodes. We're saying the conductivity is proportional to that difference, but this difference, is it the difference measured from the gamma point, or is it the difference measured from some other point in the Briand zone? And that's the ambiguity that's showing up here.
By the way,
yeah.
Maybe just to connect to
Yeah.
what I said
Yeah.
in my lecture. The very last equation in my lecture is sort of a two-dimensional version of this, where I had a partially filled two-dimensional Briand zone, and if you wrote the non-Hall conductivity as a low energy theory, which in my language was the Berry phase on the Fermi loop, it was only defined model of quantum.
Yeah.
And the quantum of and to figure out what the quantum is, you have to go to lower energies and you have to calculate the Berry curvature of all the field states.
Right.
So
That's precisely.
So, but
yeah.
since it's in two dimensions, it's dimensionless instead of having units of G. For the reason you just said.
Yeah, exactly. So that's so you see this ambiguity in terms of regularizators that actually if you look at the high energy papers, they would there was some sort of debate of what the C would be, because you can ask whether you allow for this to happen. In high energy, you don't know where you come from in high energies. You don't know how to regularize your theory. So everything is good unless you say something else. And so some unless you put some other input in your theory, like this physical fact. So some people argue that this had to be 0 because it's not gauge invariant. So depending on the regularizer, whether it preserved gauge invariance or it broke it in some ways, you can argue that this term has to be 0 and so on. But all of that is just boils down to the fact that you can add a quantum of conductivity that has, since you're in 3D, it has units of momentum and kind of changes your whole conductivity. Now, if you notice, I've just spoken about the spatial part of this C, because this C has 4 indices, has 0, and then 1, 2, 3. So obviously, a reciprocal lattice vector is only the 1, 2, 3 part. So I'm only fixing that. And in fact, you can show, or you can argue based on physical grounds that the temporal component has to be 0, because the temporal component, if you do the same calculation here, you can also find a component that looks like this, B0B essentially. So it's proportional to this. So B0B in the gapped phase. So meaning that an insulator can have, according to this, an insulator would have a current that is parallel to a magnetic field, which is pretty weird because currents are usually perpendicular to magnetic fields. And this, you can show that in equilibrium has to vanish because B0 is a parameter of the Hamiltonian, and the physical reason is that if your magnetic field is creating a current, then charges accumulate in the boundary, and this will screen that current. And so in equilibrium, the Hall effect, so this not Hall, but Hall effect, the entire effect would be 0. And this is called the paramagnetic effect, and it's only possible out of equilibrium. So since everything here we're doing in equilibrium, this has to be 0. I mean, there are rigorous ways of showing this, but I just don't have time.
That any control measurement is out of equilibrium.
Yeah. But I guess the point is that for this to be non-zero, you need something else. You need that that the two vials are filled differently. They have like opposite chemical potentials. So not 2 leads. So you always assume that you have you can have a chemical potential in the bulk of your system, like so to speak. So you assume that there's some process that equilibrates this two, and yeah, but this can only be possible out of equilibrium. And in fact, I'll show you right now why, like how can you do this in vials and connect what we just calculated to the Carr anomaly in 3D, and argue that this ambiguity is actually inherited from the Carr anomaly. So the Carr anomaly is in fact also ambiguous, but again, imposing gauge invariance. In the Carr anomaly case, you impose gauge invariance and you fix it. But here, gauge invariance is not enough. I guess because you can be gauge invariant in the bulk up to a surface term. That's why it doesn't fix it. So connection to the Carr anomaly. Okay, so I explained how the 1+1 version of the anomaly worked. So you had, you applied an electric field. Okay, let's see. So this is E, the energy is K. Apply an electric field, empty these states, populate these states. And the difference, let me say 1+1 Well, so this is, it's usually called the J5, which is just meaning J left minus J right, is proportional to the electric field. This is what I already, so this is 1 plus 1. Now in 3 plus 1, how do I get to this situation? Well, I start with 2 vial nodes, and I apply a magnetic field. The magnetic field breaks the vial nodes into Landau levels that are connected like this. I mean, you can forget about this, but this happens, right? And so if I feel the thing up to here, I go back to the same situation. It's, again, the 1 plus 1 chiral anomaly because the Landau levels don't disperse in the perpendicular direction. So I'm applying a magnetic field in the, let's say this is KZ. So I'm applying a BZ. So you apply a BZ, and you know your electrons start dispersing in the Z direction, but in the other ones they just form cyclotron orbits. Now the situation is exactly the same as this, but I have to take into account the Landau level degeneracy, which is proportional to B. So in fact, J mu 5 is E, because it's the 1 plus 1 result, times the Landau level degeneracy. And what's that? And that's essentially proportional to B. So times some factors of pi and so on. So you see that with a parallel an electric field parallel to a magnetic field induces population imbalance, and that's the mu 5 that I just, that's the let's say mu L and mu right that I need to observe the chiral anomaly. So this is the result. Now, how do I connect this to my previous results? Where is the chiral anomaly in that theory? So I want J5 to be, you know, let's try to compute this J5. So what is J5? Pictorially, you can think of it as, again, a diagram. It's actually a triangle diagram where, you know, 2 external fields come in. Let's say A mu, A nu, and you get out. Let me call it. Let's see. Let me call this nu rho, and you get out J mu 5. So if I compute this diagram, you know, I would have 2 A's. Out of those 2 A's, I'm going to construct the E and the B, and then it's going to give me a B5, a J5, and I need the derivative. So I need to multiply this by some external vector. But I have to be a bit careful because so there's some kinematics here in bold. So let's say one of the external fields has momentum P, the other one has Q, and so the Green's functions here in this loop are going to have K plus Q, K minus P, K, and so here there's going to be P plus Q. So in fact, this equation looks something like, in momentum space, it would look something like this, J5 mu equals something. And this something I'm going to call, so basically this diagram I'm going to call it, it has 3 free indices, so it's a 3 tensor that depends on 2 momenta. So it's actually P mu, Q mu, right? So it looks really similar to this thing, right? I'm just calculating the divergence on some current. I guess I'm missing some indices here because I need the 2 A's. So this is multiplied by A nu and A rho. Now I could also decide to ask for gauge invariance, and I would do like this. But this, in fact, you know, you should regain gauge invariance if you ask for this to be 0. And so, okay, so now you can calculate this diagram, and you can multiply it by P and Q. So let me call this equation 1 and equation 2. So 1 is equal to the following thing. 1 plus A 4 pi squared P alpha Q beta E mu mu rho alpha beta A mu A rho. And the second one, is 1 minus A P alpha Q beta E mu rho alpha beta, and then again mu and rho. So one has to be 0 because of gauge invariance. Because if not, I'm not conserving charge. So again, it sets A equal to 1, and it gives me a nice theory that I conserve the normal charge, but I do not conserve the chiral charge, this J5. But notice that this is an additional information that I have to put into the theory. The calculation gives me something that I can switch the anomalous contribution from one current to another by changing A. I could have chosen -1 and chose to not to conserve normal current, but conserve chiral current. But that would make physically no sense, because then we will be creating particles. So the calculation gives you a way, gives you a result, but you have to have the physical input to actually fix this ambiguity. That's what I mean, that the chiral anomaly is actually ambiguous, but once you impose gauge invariance, you recover. So it's more like the Schringer model. So it's really analogous to the Schringer model. So why was this theory ambiguous? Well, the reason is because when I calculated this guy, was G, schematically was G this. It depended on B. So this depends on B, right? So let's say I do an expansion in small b. So if I do an expansion in small b, I can write the following thing. Do I have it here? No, I have it. Let's see. Somewhere here. Okay, right. Okay. So using that J of KB is, for small b, is something like G of K of B equals to 0 plus, I think I J K of 0 gamma mu gamma 5 B mu G. So this is just the Taylor expansion of this propagator. Actually, I forgot to say that this has gamma mu, gamma nu, gamma rho. So the vertices, actually, I'm going to define this diagram right now. So gamma mu nu rho, whoops. Well, let me finish with this, and then I'll go back to that. So I'm just expanding this expression to first order in B. So I'm taking this term, and this would look like something like this. Trace of G gamma mu G. Actually, now the momenta matter. G K plus P alpha gamma 5 G K plus P K plus B, B alpha. So I'm missing something here. Gamma mu jk gamma nu jk plus b gamma alpha gamma 5 j. Okay, 3 g's and a b alpha. Okay, so you see I have 3 g's. So it looks already like that diagram, which in fact it's exactly the same expression, but instead of p and p I would have k plus p and k minus q. So what I'm setting, so this expansion is telling me that the response of a vial is actually given by the anomaly with a particular kinematic, where p, if I choose p equal to minus q, then in this diagram, then I recover this expression. Maybe that was completely confusing, but the point is that once I expand the polarization function to first order in B, this diagram appears in it, but with a particular kinematic, so with a particular choice of Q and P, in particular P is minus Q. That's all I'm saying. But if P is Q, or if P is minus Q in this equation, then this is a symmetric, so it's P alpha times P beta, contracted with an anti-symmetric tensor, so it's 0. So in this way of thinking about things, the ambiguity comes from because no matter which value of A I choose, I always respect gauge invariance. So this gauge invariance does not fix the ambiguity in this case. However, when I'm calculating the chiral anomaly, it does because I'm choosing a general kinematic. So that's so let's see, how am I doing on time? Wow, fantastic. So this is a core message. To sum up, so I have few things more to say, but the main message is that when you calculate responses of theories like this, like Lorentz breaking theories, you can encounter ambiguities that can either be fixed by gauge invariance or not fixed by gauge invariance. But if they're not fixed by gauge invariance, there's a physical reason why it's not, and it's typically the same physical reason of why, like the same physics as in the Hall effect. There's something at the boundary that's happening because the effective action is a Chern-Simons action, which I can build in 3+1 because I have this extra vector here. So usually, Chern-Simons action would be, this would be the Chern-Simons action. So in 3+1, if I don't have this guy, I cannot build it. But the fact that I have this thing makes this possible. Yeah.
What if there are no boundaries to your system? Say, there are no conditions. Does it mean that then you always get its line
Yeah. I mean, if you just
so you see it's here the boundary when it appears and it's not fixed by.
but that's yeah.
So if there are no boundaries, no problem.
If there were no boundaries, no problem. I mean, I guess the field theory is never periodic. I guess that's the question. That's one of the points that the low energy theory you always integrate up to arbitrary. So even if you never you don't have boundary. I mean,
But when you're doing that,
like
that is QED, for example.
yeah. No, in that case you have like if you're doing lattice QED, you're calculating this essentially, and you're going to get a non-ambiguous response because in the lattice is always has to be non-ambiguous. So.
And we apply boundaries conditions of humidity in a lattice? Or
Yeah. But it's just what Ivo calculated. Like if you have a lattice, your integrals run over the Briand zone, and like here, for example, your integrals run over the Briand zone, pi over a, and so you know what's the lattice vector in that way of calculating things. In this way of calculating things, you never know what's the lattice vector unless you tell the theory from the start. Okay, so now I'm gonna end with what else can you do? I mean, what can you do with this? Or what's going beyond these things? So I'm going to throw some ideas out, and then I'm going to finish. So as I said at the beginning of the first class, the point is that there are many things in high energy that might not be realized in high energy ever, like Lorentz breaking theories, for example, but can be realized in condensed matter. And using the terminology of Andre, it would be like new fermions. And so I want to make the point that some of those new fermions, many of them are new, but some of them also have a description in high energy, actually. And I'm going to choose spin 3/2. So this is I'm just going to write an action, just say that this exists in high energy as a name. Is Rarita Schringer. And it's supposed to be the action I'm going to write down. It's supposed to describe the gravitino. Don't ask me really what's that, because it's not that important. Gravitino. Yeah. I guess yeah. So I'm just going to write an action that looks a lot like stuff I've been writing already, but it's just another theory, just to make the point that, I guess this can be K, just to make the point that there is some literature on other fermions that one can realize. So if I'm not mistaken, Andre, correct me if I'm wrong, but the spin 3/2 is the fourfold? Yeah, okay. So the fourfold fermion, I think, I haven't thought too much about this, but there's definitely a spin 3/2 theory, which is that one. And I think it should describe fourfold fermions. And in fact, I think Suching's paper already calls it that way. So Rarita Schringer would be the name of fourfold fermions in high energy. But this is not true for all these new fermions, because, for example, they have there's a spin 1 fermionic threefold fermion, which, if you think of the spin statistic theorem, you cannot have a fermion with spin 1, but in this threefold fermions, it's realized. So I'm not saying everything that we can think of it's it's thought about in high energy, but there are some things that we can use from that world. And the last thing, so this is one example, and the second example is that type 2. I'm not really going to go into this because it's already very late, but type 2 is like type 2 Weil semimetals. What is that? You get the cone and you tilt it. It looks the same, but it's not really the same, because if I put the chemical potential here I would have like a Fermi surface, but here I wouldn't. So I'm just like tilting the cone. So this is type 1. This is type 2. The type 2, you can think of a type 1 plus a metric, in fact. And this is how Volovic likes to think about this type 2. And so once you start thinking about that type 2 is the type 1 plus a metric, you can go back to all the gravity books that you like and start asking what does it mean for actual experiments. And yeah, I think that's all I wanted to say. So thanks for your attention. It's gapped. I guess you can fine tune it to be gapless. I don't know. I haven't really. But just that if you take two vials and put in the same point in momentum space, you can add a mass that couples them. But I guess you can. I don't know. I haven't thought about this too much actually, but I guess you can make them gapless. I'm not sure.